Hi, everybody. It's Professor Mitchell, continuing with Chapter 2. In this video, we'll look at Section 2.4 on the inverse of a square matrix. In this section, we'll look at the inverse of A, the inverse of a 2 by 2 matrix, a matrix with no inverse, and using an inverse to solve a matrix equation. The inverse of a square matrix, A, denoted by this notation, it kind of looks like a -1 exponent, but this is read A inverse, is a square matrix with the property that when A inverse is multiplied by A, or A is multiplied by A inverse, you get the identity matrix of the same size. For example, let's verify that this matrix, 4/11, 1/11, -3/11, 2/11, is the inverse of the matrix 2, -1, 3, 4. So to do that, we'll multiply it both ways, starting like this. So notice that 4/11 times 2 is 8/11. 1/11 times 3 is 11/11, which is 1. 4/11 times -1 is -4/11. 1/11 times 4 is 4/11. So those add up to 0. -3/11 times 2 is -6/11. 2/11 times 3 is 6/11. Those add up to 0. And finally, -3/11 times -1 is 3/11. 2/11 times 4 is 8/11. And those add up to 11/11, which is 1. And you can also verify that it works in this direction also. To determine the inverse of the matrix ABCD, if the number D, capital D, which stands for determinant, there's two similar words, determinant and discriminant, and I had to think about it. Here we're using determinant. The determinant is defined to be AD minus BC. Here's a little visual aid that might help you remember what the determinant looks like. It just goes like this with a minus in the middle. A times D minus B times C. So that number has to be not equal to 0. What we're going to do is interchange A and D, which gives you this matrix DBCA. Then we're going to change the signs of B and C to get this matrix D, -B, -CA. And then finally, we will divide all entries by the determinant to get this matrix, which will be the inverse. So let's try that with this matrix. I'm going to switch over to the tablet. All right, so what do we do again? We switch these two around, and then we change the signs on these two. First, I should check to make sure that the determinant is not 0. The determinant is -2 times 7 minus 4 times -3, which is -14 plus 12. That comes out to -2. So that is not 0. So this matrix will have an inverse. So after we reverse A and D and we change the signs on B and C, what we get is 7, -2. And then flipping the signs on the other two, we get a -4 and a 3. And now we're going to divide all entries by the determinant. So I'll do that like this. And that is going to give us this matrix, -7/2, +2, -3/2, +1. Okay, so if this matrix is called A, this matrix will be A inverse. All right, going back to the presentation. Here we go. Okay, so that looks like what we did. All right, a matrix A, B, C, D has no inverse if the determinant is equal to 0. So let's quickly look at these examples to determine which matrix has an inverse. I'll put my pen on again here. -2 times 6 is -12. Minus 4 times -3 is -12. So that would be -12 minus -12, which is 0. So this matrix is not going to have an inverse. However, -2 times 6 is -12 minus 12. -12 minus 12 is not 0. So this matrix will have an inverse. All right, solving a matrix equation, my favorite thing. If the matrix A has an inverse, then the solution of the matrix equation AX equals B is given by X equals A inverse times B. So let's use a matrix equation to solve this system. -2x plus 4y equals 2, -3x plus 7y equals 7. Here's the matrix form of the equation. Now note that this matrix here is the same matrix that we already found the inverse of in a previous example. So the solution of this system will be given by A inverse times B. Here is the inverse matrix that we found in the previous example. Multiplying these two matrices together, you get -7/2 times 2, which is -7, plus 2 times 7, which is 14. -7 plus 14 is 7. -3/2 times 2 is -3, plus 1 times 7 is 7. -3 plus 7 is 4. So the solution of this system is X equals 7, Y equals 4. All right, and that's already the end of this section. We will continue with finding inverse matrices in the next section. So for the discussion in this module, if you're one of my students, feel free to show us either one of these problems. Summary of this section: the inverse of a square matrix A is a square matrix A inverse with the property that A inverse times A and A times A inverse are both equal to the identity matrix. A 2x2 matrix ABCD has an inverse if, oh, and look, they've changed the notation again. So now they're using the Greek letter delta to stand for the discriminant, the determinant, I'm sorry, get those two words mixed up, determinant. Okay. And if this matrix has an inverse, that inverse is D negative B negative C A times 1 over the determinant. A system of linear equations can be written in the form AX equals B, where A is the rectangular matrix of coefficients, X is a column of variables, and B is the column matrix of the constants from the right side of the system. If the matrix A has an inverse, then the solution of the system or the matrix equation is given by X equals A inverse times B. And that's going to do it. Nice short section this time. We'll see you next time.